In the first prototype, a simple model, you blow air into two straws which act as the trachea and bronchioles, into two balloons which represent the lungs inflating and deflating in order to represent the normal function of breathing lungs. From the first to second prototype, design changes include adding a diaphragm to solve the forced breathing problem. In the second prototype, we corrected the anatomy of the lungs by adding the ribcage, thoracic cavity. We use a bottle to represent this. We still use two straws as the trachea and bronchioles to test the air pressure. On the bottom of the bottle, another balloon was used to represent the diaphragm. The diaphragm shows the increase and decrease in lung pressure. However, the diaphragm did not work properly. From the second to third prototype, there was an error in anatomy of two tracheas. We altered it to one trachea that branches out into two bronchi. From the third to final prototype, the final prototype is one trachea and the two bronchial branches. The new diaphragm allows air pressure to increase and decrease in the lungs. The data refutes the claim of being able to support 200 millimeters of pressure because our model was only able to reach about 12 millimeters of pressure. We believe this is due to the small scale of the prototype.
The breathing process consists of inhaling and exhaling. When one inhales, oxygen enters through the nose and travels to the lungs. The oxygen then spreads to the blood. When one exhales, carbon dioxide or waste gas moves from the blood to the lungs and is expelled. When one has asthma, airflow doesn't move as freely in the lungs. The airway linings swell, muscles surrounding the airways tighten, and thick mucus clogs the airways, making it difficult to breathe. Due to asthma, the lungs receive less oxygen compared to a normal person. As you can see, the rate of oxygen consumption for the asthmatic lung demonstration is about 4 millimeters Hg.
The body requires more oxygen when treading in a lake, so the breathing rate will also rise, causing the body to take in and exhale more air. Therefore, when someone is treading water, their expiratory reserve volume will grow.
If my average breaths per minute is 15 and my tidal volume is about 0.5 liters, then my minute volume at rest would be about 7.5 liters per minute. Now, if I'm taking shallow breaths to avoid severe pain from rib fractures, and my tidal volume is about 0.2 liters, then the respiratory rate required to achieve the same minute volume as at rest is 37.5 liters per minute. Occupational hazards such as coal dust, silica dust, and asbestos leads to the scarring of lung tissue, and the lungs would become stiff and have more recoil. So this would cause a lack of ability to inhale and restrict inflow. Due to the lack of ability to inhale, both TLC and VC would decrease.